With the power of my momentum ray gun, I'll be able to destroy everyone's momentum. No one will ever be able to move ever again.
Oh no, what will they do? Look, the hero of PhysicsTown, linear mv equals p, has come to save the day.
You will never be victorious. I will make the velocity of your plan 0.
If I destroy your momentum, you won't ever be able to even make a move against me. Pew.
Wait a minute, is that really how momentum works?
First of all, what is momentum? Linear momentum, which is denoted by p, is defined as the product of an object's mass times its velocity. Therefore, momentum is a vector quantity with both direction and magnitude, and its direction is in the same direction as the velocity component. Its units are in kilograms times meters per second. Finally, since momentum depends on velocity and velocity depends on reference frame, momentum is also affected by reference frame. For example, from the inside of the car that you are sitting, it may seem like the car has no momentum, but from an outsider's point of view, the car very clearly has velocity and momentum. So, why does Evil Bob want to destroy everyone's momentum? Well, momentum is incredibly important in most facets of life. The transfer of momentum allows us to travel around, move things, and so much more. With Evil Bob's wicked scheme, the world will be frozen. Or will it? Let's learn more about momentum and see. Let's say that an object A is exerting a force on an object B. Both objects are in space, and we will use distant stars as our reference point. Because of Newton's third law, the force of object B on object A is equal to the opposite of the force of object A on object B. Additionally, since the forces of objects A and B on each other are the only forces acting on either object, we can use Newton's second law, which states that the net force acting on an object is equal to the object's mass times its acceleration, to create additional equations. In the case of the force of object B acting on object A, we can say that the net force acting on object A is equal to the force of object B on object A, but that the net force of object A is also equal to the mass of object A times the acceleration of object A. We can also follow suit with the force of object A on object B for object B, where the mass of object B and the times the acceleration of object B equals the net force acting on object B, which equals the force of object A acting on object B. Substituting them into the above equations, we get that the mass of object A times the acceleration of object A equals the opposite of the mass of object B times the acceleration of object B. Next, since the acceleration of an object is equal to the change in an object's velocity over the change in time, we can substitute this equation into both of the above accelerations, which leaves us with the mass of object A times the change in the velocity of object A over the change in time, equaling the opposite of the mass of object B times the change in velocity of object B divided by the change in time. Afterwards, we can multiply both sides of the equation by the change in time, leaving us with the mass of object A times the change in the velocity of object A, equaling the opposite of the mass of object B times the change in the velocity of object B. Afterwards, since the change in an object's velocity equals its final velocity minus its initial velocity, we can substitute the final velocity minus initial velocity for both of the changes in velocity for the two equations, which leaves us with the mass of object A times the final velocity of object A minus the initial velocity of object A, equaling the opposite of the mass of object B times the velocity of object B minus the initial velocity of object B. Next, we can distribute the masses on both sides of the equation to get the mass of object A times the velocity of object A minus the mass of object A times the initial velocity of object A equals the opposite of the mass of object B times the velocity of object B plus the mass of object B times the initial velocity of object B. Next, we can add the negative parts of either side of the equation to both sides of the equation, leaving us with the mass of object A times the velocity of object A plus the mass of object B times the velocity of object B equals the mass of object A times the initial velocity of object A plus the mass of object B times the initial velocity of object B. Additionally, since we established earlier that the momentum of an object equals an object's mass times its velocity, we can convert all four of these numbers into momentums, leaving us with the final momentum of object A plus the final momentum of object B equaling the initial momentum of object A plus the initial momentum of object B. Finally, since one side of the equation shows the sum of the final momentums of all objects in the system, that sum is equivalent to the total final momentum of the entire system containing objects A and B. The same goes for the other side of the equation, but for the initial momentum of the whole system, leaving us with our final equation of the final momentum of a system equals the initial momentum of the system. With this equation, we have proven the law of conservation of momentum. In any isolated system, when two objects collide and change each other's momentum, the total momentum of the system remains unchanged.
For our conservation of momentum lab, we tested 4 types of collisions to see if the conservation of momentum would remain true for various trials. For all of these trials, we used a lab quest and 2 motion detectors on either ends of the rail to record initial and final velocities of the 2 cars. An important thing to note is that we measured velocities headed toward the 0 on the rail as negative, and the velocities directed towards the 120 on the rail as positive. Now, onto the collisions. Our first type of collision was an elastic collision. We made sure that the magnetic sides of the 2 cars were facing each other, and the cars would bounce completely when they collided. The next type of collision was the completely inelastic collision. We made sure that the 2 Velcro sides were facing each other and the cars would stick together and continue traveling in the initial direction of the car with more momentum. The third type of collision was the inelastic collision. One car had Velcro and the other car had its magnetic side facing the other in these trials, and the results were a mix between the other collisions. Finally, our last type of collision was the explosion. In this collision, both cars began with a velocity of 0, and then we would press a button on one of the cars to release the spring, which would cause the cars to burst away from each other. Altogether, our data resulted in a slope of 0.9024, which is only about 10% away from the expected value of 1, since the 2 momentums would theoretically be equal, and therefore when plotted against each other should reveal a slope of 1.
Another important physics concept is impulse. In physics, impulse is defined as the product of any external force exerted on an object during a time interval and a time interval. So this can be represented in an equation as average force times the final time minus the initial time, which is also known as delta t, equals the impulse. For example, when you hit something with a bat, an external force is applied to the ball over a short time period, so an impulse is applied. Additionally, a greater time interval will result in a greater impulse, which is clear when looking at the equation. So if the time interval is longer, that will make the impulse greater. An interesting case that exemplifies this is if you consider shooting a bullet at a door versus pushing it. Though the bullet applies a much greater force on the door than your hand, the bullet will not open the door in most cases. This is because the bullet only applies the force for a very short time, since it rips through the door, while your hand can apply the force for a longer period of time, and therefore result in a larger impulse. To start our impulse lab, which the objective was to show that the change in momentum equals the impulse. We set up an experiment where we used a force probe to measure the force the cart hits the end of the track with, and we also used a motion detector so we could calculate the speed of the car at the same time. So we put the car on the track, and on one end we set up the force probe, and the other side we set up the motion detector. We also measured the mass of the car before starting the experiment. We then connected both instruments to the lab quest before we started taking data. Then when we pushed the cart towards the force probe, we did it with different speeds, so we were able to demonstrate that it did not matter what the initial velocity of the cart were. In the end, the impulses would still equal the change in momentum. Then we pushed the cart towards the force probe and used a lab quest to measure the average force of the collision and the time interval of the collision. So with those values, we were able to use this equation here to find the impulse. At the same time, we use the lab quest to calculate the velocity of the car before the collision and after the collision. So we were able to use the equation that momentum equals the mass times the velocity. And then we were also able to calculate change in momentum, which would equal m2 v2 minus m1 v1, where m1 and v1 are the mass and velocity before the collision, and m2 and v2 are the masses and velocities after the collision. And like I said earlier, change in momentum equals the impulse. Here I will show you why this is true. So as I stated before, average force times the final time minus the initial time equals the impulse. And then we also know that the average force equals ma. That would mean the average force over m equals a, and we can rewrite that as the average force over m equals the final velocity minus the initial velocity over the final time minus the initial time. So this equation right here can be rewritten as the average force times t final time minus the initial time equals the mass times the final velocity minus the mass times the initial velocity. And as I said earlier, P equals mv, so the momentum equals mv. So this right here is saying P final minus momentum initial equals the change in P. So if you rewrite this equation here, that's saying the average force times final time minus initial time, which is also known as J, which is impulse, equals this right here, change in momentum. So the impulse equals the change in momentum. So from our experiments, we were able to calculate the impulse and the change in momentum. And since the change in momentum equals the impulse, if we were to graph these found values on a graph, then the slope of the line should equal 1. So after calculating our values, we plotted them on a graph. So you can see the y-axis is the impulse, and the x-axis is the change in momentum. And our slope was 0.9432. So as I said, theoretically the slope of this line should be 1 because change in momentum and impulse are the same. But for our experiment, we had a source of error that came up to about around 10%. And some causes of these errors may have been that the lab quest may not have been 100% correct in calculating the given values. Another source of error that may have skewed our results is when we pushed the car, it shook the track a bit, so there may have been additional forces that acted on the car that affected its speed. And also the force probe we used was shaking as well when it was hit by the car, so it wasn't a direct force acted on the probe by the car, and there may have been additional force that would affect how it was calculated on the lab quest.
Cool. Okay, so that's how momentum works. But wait a minute. If momentum is conserved,
Then he cannot be destroying our momentum. He can only redirect it into his ray gun. So if I destroy the ray gun, it will release all that stored momentum and transfer it back to him.
What have you done? No, no!
with the power of physics and the conversation of momentum, linear mv equals p saves PhysicsTown once more.
Yay!
Yeah!